Hello, this is Connor from KAIST, and I'm very happy to be here and introduce our paper Redactor, which is a data-centric and individualized defense against inference attacks. Recent machine learning researches found that there are various kinds of privacy threats during model training, so protecting the models from these threats becomes one of the important directions for trustworthy AI research. Many companies like Microsoft, IBM, Facebook, and Google emphasize the importance of the trustworthy AI, and they suggest their principles for it. They are slightly different from each other, but they have common main directions, and they include privacy and security, as well as fairness and explainability. In real-world applications, most machine learning models focus only on the performance, so it makes the models more vulnerable to privacy attacks. Exploratory attack is one of the adversarial attack techniques that extract information about the victim ML system. And among them, the membership inference attack is the most popular technique. It is an attack that guesses whether specific data is used for model training through the output value of the victim model, and is also used to test the privacy of the models in privacy-preserving ML tools like TensorFlow privacy. Other attacks include the inversion attack, which reconstructs the input data using the model and the output. I will now briefly explain membership inference attacks, or MIAs. Let us assume that a victim collects data from the public, labels the data, and trains a model on the labeled data. An MIA uses the model's output, including the loss values, to classify whether a certain data is a subset of the training data, which is why we call this a membership inference attack. To do this, the attacker trains a binary classifier that takes the model output as its input and predicts membership. Existing defense techniques against membership inference attacks often assume that the victim shown here has full access to the model training process, which makes sense if the victim owns the model. An effective strategy is then to directly add noise to the model's output, and thus make the membership inference more difficult. However, we assume the setting where the victim does not own the model, and thus has no access. Moreover, we assume it is difficult or impossible to delete information that is published to the web or uploaded on a third-party platform. In this case, the existing defenses are no longer usable. The only solution is to take a data-centric approach and add new data that dilutes an individual's personal information, which we refer to as disinformation. We thus define the problem of targeted disinformation generation, where the goal is to generate disinformation that indirectly makes a victim model less likely to leak personal information to an attack model without any access to the victim model. I will now explain our problem definition using a simple example. Suppose a victim model is being trained on people data to classify them into low versus high income classes. Let us assume there is a target person whose information we want to protect from membership inference attacks. In order to construct the training data, a human labeler could be used to label each data point, as in this figure. The human labeler will effectively have a decision boundary like the one shown here. Let's assume we know this decision boundary for now. Then our approach is to insert fake data that is called disinformation, like these X points that can manipulate the decision boundary, so that the classification accuracy and confidence on the target decrease. However, in our setting, we cannot access the human labeler and thus need to estimate the decision boundary instead. Our solution is to generate a probabilistic decision boundary instead. The idea is to use several classifiers as surrogate labelers and combine them as each one of them may not be as accurate as a human labeler. This approach is inspired by ensemble techniques that are commonly used for forging black box attacks. We use data programming techniques to combine the surrogate labelers into one generative model. We then use the decision boundary of the generative model conservatively to choose disinformation points that have a different class than the target, but are similar looking to the labeler. Please see our paper for the mathematical details. To find candidate disinformation points, we utilize a set of base points that are known to be in a different class than the target. The first technique we use to generate points is watermarking, where the idea is to take linear interpolations between the base points and the target, and choose the points near the probabilistic decision boundary. This technique is commonly used in targeted adversarial attacks on image data. We also perform clipping and quantization to make attribute values have discrete or categorical values when necessary. Another technique we use to improve the candidate disinformation points is to generate more bases using GANs. In our work, we use a CT GAN for tabular data, but other GANs can be used as well. However, GANs are not perfect, and some of the generated bases may not be realistic, as we illustrated in the slide. So we also filter out generated points that contain infrequent patterns in original data. So the overall process of disinformation selection works as follows. After generating realistic candidates, we choose the points closest to the target while still beyond the probabilistic decision boundary. These disinformation points can be released to the public and potentially added to the training set used by victim model, lowering its performance on the target. I will now show how our Redactor framework performs using two representative experiments. Recall we assume the following workflow where disinformation is added to protect the victim model from attacks. Experiments 1 and 2 will show how our disinformation affects the victim model and the attack model, respectively. In our paper, we also have more experiments on using probabilistic decision boundaries and scalability. We use 3 benchmark datasets that contain personal information. We measure the performances on the target and entire data separately, where our goal is to only reduce the performance on the target. We evaluate Redactor's disinformation in terms of how it lowers a victim model's accuracy and confidence on the 3 datasets. We repeated evaluations on 13 victim models per dataset and show the average performances. As a result, the target accuracy and confidence both decrease significantly, as highlighted in bold font, while the overall accuracy does not decrease much. As a comparison, we also show the result of CPA, which is a state-of-the-art data poisoning technique. CPA is much less effective because it assumes that pre-trained weights are available and relies on a fixed feature space, whereas our method assumes a more general setting where this is not always possible. The second experiment is to directly measure the performance of membership inference attacks with disinformation. We use the most common MIA in the Redactor, and experiments on other types of MIAs can be found in our paper. We evaluate on 9 attack models in the paper, but I bring 4 representative results as shown in the table. As a result, the disinformation causes the target accuracies of the attack models to fall by up to 22% and become close to 50%, which means the membership predictions are not useful. In summary, we proposed disinformation generation around a target as a way to protect one's privacy against membership inference attacks when the victim model is inaccessible. In our experiments, we showed how our disinformation lowers the victim model's target performance without lowering the overall performance much. Consequently, we also show that membership inference attacks became much less effective as well. Thank you for listening.